We're going to graph tangent similarly to the way we've done sine and cosine. One thing I want to let you know is that the graph, or that the tangent function is actually, if you took the sine function and divided by the cosine function. So the reason this is relevant to us is because sometimes the cosine function equals 0. And wherever the cosine function equals 0, it would mean we're dividing by 0, and therefore the graph won't exist there. So the sine and cosine functions were both continuous functions, meaning they were just these waves that repeated over and over again. But the tangent function is going to be a little different. There are actually going to be spots on the graph where there is no graph. There are going to be asymptotes on this graph. So I'm actually not going to go through this table and tell you what all of these values are, because the graph is going to look a little different. So far, sine and cosine had started at 0, and then usually when we graph one cycle, it goes off to the right. The tangent graph is actually centered at 0, meaning it goes into negative x values and positive x values. So our standard values that we're always going to have on our graph, unless the period changes or we have a phase shift, are going to be negative pi over 2 and positive pi over 2. That's going to be our normal start and stop numbers, and those are actually going to have asymptotes at those numbers. So they're going to be undefined. And then in between those, we're going to have 3 points, negative pi over 4, 0, which I don't have to really label, and then positive pi over 4. So everything's going to be symmetric. Whatever is, as long as we're centered at 0, you're going to have the 2 asymptotes, and then you're going to have 2 more points that are going to be halfway in between, and then you're going to use 0. Okay, now the cosine graph, the tangent graph, for the parent graph, we're going to label up to 1 and down to negative 1. And then here's what's going to happen. We're going to have a point at pi over 4, 1, 0, 0, and then negative pi over 4, negative 1. So it almost looks like it makes a diagonal line, but the way we're going to connect it is going to look something like this. So it's going to be a curve. As you go up to the right, it's going to approach that asymptote at pi over 2, and as you go down to the left, it's going to approach the negative pi over 2 asymptote. So what I want to do is kind of make my own table here. So we'll do our angle, which is going to be our theta, and then the tangent of theta. So we're going to make our own little table. We're not going to use this one right here. So the first one, the first point, our normal point is going to be negative pi over 2, followed by negative pi over 4, 0, and then the positives of those same angles. And then at the end points, so at our negative and positive pi over 2, that's where the asymptotes are going to be. So those are going to be undefined values. If you tried putting it in your calculator, it would give you an error. At negative pi over 4, your y value is negative 1. At 0, it's 0. And then at positive pi over 4, it's positive 1. So these are the standard values, the ones that you're going to need to have memorized. It is quite a bit different. The graph definitely looks a lot different than sine and cosine. So this is something you're going to have to really commit to memory. Let's talk about the default values for tangent. That is, what are the default values for the parent function, which is y equals tangent x. The domain is a little bit tricky. In sine and cosine, it is all real numbers, and then we were kind of looking at just the interval of the one cycle we were graphing. The domain of tangent is tricky because of those asymptotes. Those are all places where the x values are not defined. So for our purposes, what we're going to do is talk about just the domain of one cycle of the tangent graph. The tangent graph starts at negative pi over 2, and it stops at pi over 2. But since those are asymptotes, those are places where the values are not defined, that means we're not going to include those values, meaning we're going to use parentheses instead of brackets. Now the range is interesting too, because with sine and cosine, they went up to 1 and down to negative 1, and then they just oscillated back and forth between those two values. But for the range of tangent, because our graph looks like this, where it goes up and down forever. So the range of tangent is actually all real numbers because it goes on forever and ever up and down. Now, because that happens, it goes up and down forever. This graph actually will never have an amplitude. So under amplitude, I'm going to put none. And the reason is because it's already infinitely tall. It goes on forever and ever, up and down. So there's no way to say that you're making something twice as tall or half as tall if it goes on forever and ever. For the same reason, or similar reasons, there is no midline. Because who's to say where the middle of something that's infinitely tall is? So there will never be an amplitude and there will never be midline for tangent. Now the period, I'm going to put a star next to this one because the period is different than it is for sine and cosine. The period for sine and cosine was 2 pi. The period of cosine is only pi. So that's something that's going to be a little bit different that you're going to have to be careful to remember that it is different. Now I want to take a look at the equation down here in this box, and I want to talk about what all these letters do. It's all the same letters that you remember seeing with sine and cosine, but they're going to be a little bit different. You can still have an a value. That a value can still be a negative for a reflection, and it can also be a stretch. It is no longer going to be our amplitude because, as we discussed above, there is no amplitude. But you can stretch the graph out and make the shape of it look a little bit different. So I'm going to write that this would be your stretch. B still tells you the period. It doesn't tell you period, but it's how you get the period. And there's a new formula that we're going to use, and that is pi over b. So it's the same formula, but you just have to remember that the period of tangent is pi instead of 2 pi. Your h number does the same thing. It moves your graph left and right. So this is still your phase shift. And then your k number, even though we don't have a midline, it still can shift your graph up and down. So it can take those 3 points that we plot and it can shift them up and down, but there's never going to be a midline that cuts it in half like we drew in with sine and cosine. So at the bottom here it says, in case you didn't notice, the period of tangent is different from sine and cosine. And then this formula that I wrote up there in blue, this pi over b, that's going to be the new formula that you have to remember is used only for tangent. Now we're going to be given graphs and we need to identify the key features that it asks us to identify. So for number 1, actually let's go through and do each feature for all the problems at one time. So the first thing it asks us to find is amplitude. If you remember from the previous slide, I said that tangent will never have an amplitude because it goes up and down forever. So you can't make something twice as high if it's already going to infinity. So this is almost a trick question. So all of these, the answer is going to be none. It doesn't matter, like if you look at number 2, it does not matter that it has a 2 in front. That's no longer amplitude, that's just a stretch. It's just telling you that those 3 points that we're going to graph are going to get stretched out. So they'll be twice as far away from each other, but it's not going to change an amplitude. And then same thing for number 4, this 3 does not represent an amplitude. It represents that those points are going to get stretched out 3 times farther apart from each other. All right, the next thing is the shifts. So we're talking about horizontal shifts and we're also talking about vertical shifts. Horizontal shifts would be your H number. That would be the number in parentheses. So for number 1, I don't see any horizontal shifts because there are no parentheses. And actually, I don't see any horizontal shifts in any of the problems. None of them have a phase shift. So I don't have to write anything about horizontal shifts. But I do have to worry about vertical shifts, and that is your K number. So since there's no K number in number 1, it's like there's an invisible plus 0. It means that there are no shifts. So I'm going to also write none. For number 2, same thing. I don't have a K number, so there are no shifts. For number 3, there is a K number, and it's this 2 right here. Since it's positive, it tells me that this whole graph is going to get shifted up 2. Now remember, it is not a midline. We're not going to have a midline for tangent. It's just saying that those 3 points we're going to graph are going to get shifted up 2 from where they usually are. And then for number 4, I have a K number of -1, so this graph is going to get shifted down 1. Now the last thing we have to talk about is the period of each graph. So period is using that b number, and remember that there's a little formula, and that is period is pi over b. So in number 1, our b number is 2, so the period would be pi over 2. In number 2, our b number, it looks like it doesn't exist. So what that actually means is that b is 1, and it actually means that the period is not going to change from the parent function. So you can actually write it out, pi over b, pi over 1, but that's still pi, which is the standard default value for the period of the tangent graph. Number 3 is the same. There's no number in between tangent and x, so that means b is 1, which means the period will remain pi. And then for number 4, we have a b value of 4, so the period will be pi over b, which is pi over 4. We're now going to write equations given some information about the graph. So the first thing it says for number 1 is that there's a vertical stretch of 2. So that 2 is going to represent our a number. And then it says shifted up 3, and that represents our k number. So our equation is going to look like this. A always goes first, and then I'll have tangent x. I don't need to have anything in between tangent and x. That would be only if there was a period change. And then shifted up 3 is our k number, so I'm going to put plus 3 at the end. For number 2, I'm going to do kind of the same thing. I have this reflection, which is affecting our a number. It means that we're going to have a negative very first thing. Phase shift of pi over 3 to the right, that is our h number. And then shifted up 2 is again our k number whenever you have a vertical shift. So we're going to have y equals negative, that's our reflection. There's no stretch number and no period change, so it's just going to be tangent x. But I do need to have parentheses for my phase shift. Since it's going to the right, that actually means I'm going to use a minus because it's always going to be opposite. So it's going to be minus pi over 3 and then shifted up 2, so plus 2. For this graph, the only thing that's changing is that it is being stretched by 3. Since the period is not changing, because the b value here is 1, that means period is pi over 1, or just pi, which is the regular standard default period for a tangent. Since it's not changing, I can automatically put in the x values that you should have memorized. Negative pi over 2, negative pi over 4, positive pi over 4, and positive pi over 2. So I'm going to put a little note here. Since the period equals pi, and it does that because there's no b value that's different from the standard, that means you can use the normal x values. All right, so I'm going to go ahead and draw in the asymptotes here at negative pi over 2 and positive pi over 2. And that's actually one of our questions. I'm going to go ahead and write this, negative pi over 2, positive pi over 2. Okay, now we have this stretch of 3. So normally the graph goes up to 1 and down to negative 1, but those points are going to get stretched. So instead of being 1 unit apart, they're going to be 3 units apart. So I'm going to have to go up to 3 and down to negative 3. So let's plot our points here. So we're going to go positive, positive. So that means right to pi over 4 and then up to 3. 0, 0. And then left to negative pi over 4 and down to negative 3. So my first point is positive, positive, 0, 0, negative, negative. And now I can connect the dots to complete my graph. Now over on the right side, we already figured out period is pi. And the amplitude is a trick question. Remember that tangent graphs do not have an amplitude, so the answer is none. And the reason is because it goes up and down infinitely, forever and ever. So there's no way to say how far above or below a certain middle point that it would go. I'm going to change question 3 just slightly. The only thing I'm going to do is add in a negative in front because I want you to see what it looks like when you have a negative reflection here. So the first thing I see, there are 2 changes. One is this reflection that I just added in, and that's going to affect our y values. And then I also see that there is a b value of 1/6, and that's going to affect the asymptote values. So when you have a change in your x values, meaning that you have a b value that's changing the period, what we're going to do is we're going to use a little miniature formula to figure out what the new asymptotes would be. So I'm going to show you a little formula here. And I'll explain what this is in just a second. So bx equals negative pi over 2 and bx equals pi over 2. So the bx is referring to whatever the number is that represents your b and then your x value. So in this problem, we're going to have 1/6 x equals negative pi over 2 and 1/6 x equals positive pi over 2. These things right here, the negative and positive pi over 2, these are your regular asymptotes, or your normal asymptotes. So the ones that go with the parent function. So you always set your b value with x equal to the regular asymptotes, and then we're going to solve it. When you solve it, the easiest thing to do is always to multiply by the reciprocal of what's next to x. So right now, 1/6 is next to x. The reciprocal of that is 6 over 1. So I'm going to multiply that on both sides. It's going to cancel everything out next to x, leaving me with x by itself. And then if I multiply straight across, negative pi times 6 is negative 6 pi. And then 2 times 1 is 2. And then if I simplify this further, negative 6 divided by 2 is negative 3. So my first asymptote is at negative 3 pi. And then my second asymptote, I don't have to solve it again because I'm going to get the exact same answer, but I'll get the positive version of that answer. So my other asymptote is going to be at 3 pi. So what's nice about this is that you're really only doing half of the work because everything's always going to be symmetric. Whatever your asymptote is on the left side, it's going to be the positive version of that on the right side. So I can go ahead and put in my dotted lines. Now to find the middles, meaning these points right here that are halfway between the asymptote and 0, what we're going to do is take our asymptote and divide it by 2. We're going to cut it in half. So to find the middles, you're going to divide asymptotes by 2. So if I divided negative 3 pi by 2, I would have negative 3 pi over 2. And then positive 3 pi over 2 on the other side. All right, so now I am set to go with my x values. I do not have a stretch, so what that tells me is that my y values are going to be at 1 and negative 1. But that reflection tells me that I am going to have to reflect. Well, obviously. The reflection tells me that I'm going to have to take those points and reflect it over the x-axis. So I'm going to put in yellow. My normal parent function values would be positive, positive, so that would be up here. So if I reflected that, if I changed the sign, instead of being at positive 1, it's going to be down here at negative 1. And then 0, 0, if you reflect it, it stays in the same spot. Now your other point usually is a negative, negative, so it's down here. But again, we're going to reflect it by changing its sign, and it's going to go up here. So it's going to be the same shape of graph, but now it kind of looks like it's backwards. It's just because it's reflected. All right, so period. There's two ways you can figure this out. The first way is by looking at the graph. If you see that from this side here to 0, it's 3 pi, and from this side here to 0, it's also 3 pi. If you added these together, it would give you a total of 6 pi, which is the period of this graph. The other thing you could do is use that formula, the pi over b. So if I did pi over b, that's pi over 1/6. Because I have a fraction and a fraction, I have to flip and multiply by the reciprocal of the bottom. And then pi times 6 is also 6 pi. So either way you look at it, the period is 6 pi. Amplitude is another trick question. And the answer here is that there is no amplitude. And then asymptotes we figured out at the very beginning. Those were x equals negative 3 pi and x equals positive 3 pi. Even though this is example 1 in our notes, I'm actually going to change the problem a little bit, and you notice that it's at the end of the PowerPoint instead of the beginning. I'm going to change this a little bit so that it looks more similar to things you're going to see on your homework, things you'll see on the review, things you'll see on the test. All right, so first thing I want to point out is that there are two changes to the parent function. The first thing is that there's a b value, which is 3. So that tells us that the period is going to change, which is then going to change the asymptotes. And then I have a +1, which is our k value, and that's telling me that the graph, everything is going to get shifted up 1. So the first thing I want to do is remind you about the asymptotes and how we're going to figure those out. So we're going to set up two equations, bx equals -π/2 and bx equals +π/2. And in this problem, our bx is actually going to be 3x. So I'm going to say 3x equals -π/2 and 3x equals +π/2. Now, even though we have two equations, we're really only going to be solving at one time because they'll be the same answer with opposite signs. So in order to do this, what I'm going to do now is multiply both sides by 1/3. You might be thinking you want to divide by 3 to get rid of that 3 in front of x, but this is the same thing, and I think it just looks easier to multiply a fraction times a fraction as opposed to dividing by a number and then having that fraction in a fraction thing. So I think this is the best way to do it, is just to always multiply by the reciprocal. So these 3's cancel out, leaving me just with x. And then if I multiply straight across, I get -x, and then 2 times 3 is 6. So that tells me that my other asymptote here would be +π/6. So I can go ahead and write -π/6 and +π/6. And these are going to be the asymptotes of the graph. So I'm going to go ahead and draw those in. So I have dotted lines right here. Now to find out the numbers that go in the middle between the asymptotes and 0, so that would be this mark and this mark, what we're going to do is take the asymptotes and we're going to divide them by 2. But what we're really doing is we're multiplying the denominator by 2. So if I take this and I multiply it times 2, that would give me -π/12. So that would be this middle. And then exact same thing here, multiply it by 2, that gives me +π/12. So that's this mark here. And then 0 is always going to be our middle, so we now have our 5x values. All right, so the next thing we need to talk about would be our y values. Now normally we have a point at 1, 0, and -1. That's going to be a little bit different now though, because the whole graph is getting shifted up 1. So even though officially there is no midline, what I'm going to do is I'm going to draw just a very light dotted line here at 1, and that's going to be my new middle. So I'm going to write here, it's not a midline because this thing goes, it's infinite, so there's no way to say where the middle is, but I'm using this kind of as a guide so that I know where my 0 point should be. So if I put my 0 point right here, and my stretch is only 1, so I'm going to have to go up 1 and down 1. So I would have to go positive, positive. So I'm going right 1, up 1 from that middle point, and then negative, negative. So now I'm down here. So this would be my graph here. And one thing I want to show you, so what I'm about to do is not actually part of the real graph, but normally our points look like this. We have a point here, and then a point down here, which would be at -1. And if you look at all of my new points, it's the same as the old points that just got moved up by 1. And that's all we're doing, is we're shifting all of our regular points up by 1. Now the next question is, what are the zeros? There is only one. It only crosses the x-axis at one point, which is right here at -π/12. So our 0 would be -π/12, 0. The domain of this graph, it starts at -π/6 and it stops at +π/6. But there are no points on the asymptotes, so we're going to use parentheses. And then the range goes up and down forever for our y value. So the range is actually all real numbers.